All right, this is section 12-1, chapter 12. This is recording number 2. Okay, the author mentioned that there's all kinds of things that the F-test can do, and what we're going to focus our attention on is just this one right here, the one-way analysis of variance technique to determine if there is a significant difference among 3 or more means. Okay, so if you only have 2 means, you use the techniques that we learned in chapter 8 and chapter 9. Or actually, I'm sorry, it'd be chapter 9. So if it's just 2 means, we would do what we see in chapter 9. If it's 3, 4, 5, 6, and so forth means, then we're going to use the analysis of variance. Okay, so the one-way analysis of variance is used to test the equality of 3 or more means using sample variances. Now this seems strange, does it not? Why in the world are we using variances to test the equality of 3 or more means? Okay, it's a little bit beyond the scope of this class to prove that this works, so we're going to just have to accept it as being a legitimate technique. Okay, all right. So he talks here about, well, what this procedure is. There's only one independent variable, and he gives a new name for the independent variable. Sometimes we call it a factor in this context. Now he's talking here and he says, well, okay, why are we doing this? I mean, if you have 3 or 4 means, why don't we just compare them? We'll use the t-test to compare 2 means at a time, for example. Okay, if we don't know the variances of the population, we can just use the t-test, right? We've done this before. Well, there's a few reasons why we don't do that. If you have 3 or more. If you only have 2, then you absolutely use the t-test. If you have 3 or more, you're going to use the analysis of variance. Well, here are the reasons why. First, when you're comparing 2 means at a time, the rest of the means under study are ignored. Whereas with the F-test, all the means are compared simultaneously. The second thing is when you're comparing the 2 means at a time and you're doing these so-called pairwise comparisons. So pairwise means let's say you had 5 guys that you were checking. Okay, we're going to call them X bar 1, X bar 2, X bar 3, X bar 4, X bar 5. Okay, so you compare X bar 1 to X bar 2. You compare X bar 1 to X bar 3, X bar 2 to X bar 5, and so forth. All of those are called pairwise comparisons. The probability of rejecting the null hypothesis when it is true is increased, since the more t-tests that are conducted, the greater is the likelihood of getting significant differences by chance alone. So just by mere chance, you could reject by mistake, right? You could be wrong. Well, the more of these tests that you do, the more likely it is that you make that sort of mistake. Third, the more means there are to compare, the more t-tests are needed. For example, for the comparison of 3 means, 2 at a time, and so forth and so on. So I'll let you read that, but here I figured, let me show you how they come up with this. For the comparison of 10 means, 2 at a time, 45 tests are required. Now, where does that come from? How do we know that? Okay, so that paragraph I was just reading was on page 646 of the section of the edition number 10. So this is a note about that page. For comparison of 10 means, 2 at a time, 45 tests are required. Where does that come from? Well, this is an example of combinations that we discussed in section 4-4, page 232. Now, the reason this is a combination as opposed to permutation is because we don't care about the order. We're not arranging them in any particular order. We're just comparing, for example, X bar 1 to X bar 6, X bar 3 to X bar 7. We're making the comparison. We don't care which one. There's no particular order that we need to be concerned about. Therefore, it's a combination, not a permutation. Well, I hope you remember the formula from that. Here it is N choose R combinations. Here's the formula. Okay, so in this particular case, if we had 10 guys, 10 X bars that we're looking at, and we take them 2 at a time, how many would there be? Well, on top it would be 10 factorial. On the bottom it would be 10 take away 2 factorial. That's 8 factorial, and then 2 factorial. Okay, so 10 factorial divided by 8 factorial. Remember, the first 2 guys live, so it's 10 times 9 divided by 2 factorial. 2 factorial is just 2 times 1, so that's just 2. So 10 times 9 is 45. Divided by or I'm sorry, 10 times 9 is 10 times 9 is 90, divided by 2 is 45. Okay, so that's where that number comes up. And then the same exact process would be used to calculate the other ones that the author mentions. So let me see if I can close this now. Hope I don't screw this up. Okay, so that's what he's talking about here. All right, as the number of populations to be compared increases, so if you have 10 medications that you're looking at, or 100 medications, the probability of making the type 1 error using multiple t-tests for a given level of significance also increases. Okay, what's the difference between this and what he set up above? You know, I don't see, there's really no distinction. A type 1 error is this. This is the type 1 error. The probability of rejecting the null hypothesis when it's true, that is a type 1 error. You reject it when it's true. And then he says the same thing down here. The only thing he says differently is he says for a given level of significance, alpha also increases. Well, you know, hey, the author's human too. Maybe that's just a surplusage, just an extra sentence that it doesn't really need. Okay, so in order to address this problem, we use this analysis of variance. Okay, so what do we use? We're going to use the F distribution, the F probability distribution. And here are the properties of the F probability distribution. Okay, I'll let you read that. That's the same as the discussion we had in chapter 9 about what the F distribution is all about. Okay, the key thing is the family of curves is based on the degree of freedom. Okay. All right, and then here's a key point. Even though you're comparing 3 or more means, you're looking at the means, we're going to use the variances are going to be used in the test, not the means. Now that's very counterintuitive, goes against what what your common sense tells you. However, that's just the way it is, okay? All right, so now this paragraph right here is the most confusing paragraph in the book, it seems like to me. The only hope is you've got to follow along here very carefully, and you need to have in your mind at every moment, you've got to have a concrete example. A concrete example will make this more clear, okay? The other thing that's a problem is prepositions. You remember what prepositions are, okay? Between and within. Okay, what the heck is the distinction here between group variance and within group variance? What in the world is he talking about? Now you'll see in a minute that the first one, the between group variance, actually is a little more intuitive. It's pretty easy to understand, I think, compared to the within group variance. Okay, it makes you crazy. So let's look at an example. Let's bounce down here to an example. Give me 1 second. Okay, so before we even look at the formulas or do the calculations, let's just get this example really in our heads, okay? Miles per gallon. The researcher wants to see if there's a difference in the fuel economy for 3 different types of automobiles. So the types of automobiles, those are your groups, okay? Group small, group sedan, group luxury. And again, these are metaphors. This could be group medicine 1, group medicine 2, group medicine 3. He randomly samples okay, he has 4 in this first group, 5 in the second group, and 3 in the third group. So there's 1, 2, 3, 4 in the first group. There's 1, 2, 3, 4, 5 in the second group, and so forth. Okay, so these are the groups. Okay, and we get certain information. And again, this could be, doesn't have to be miles per gallon. It could be how many days in the hospital before you're discharged. Okay, all right, and then at alpha equals 0.05, so our error budget, how much of a risk are we willing to take of being wrong, is 0.05. Test the claim that there is no difference among the means. So our null hypothesis is that the averages, the means, are identical. They're mu1 equals mu2 equals mu3. Okay, so here's the raw data. Here's our claim that they are equal. The research hypothesis, the alternative hypothesis, is that at least one of the mean is different from the others. Okay, so we got to find the critical value. So all of this, in order to do this part, we need to understand the formula. But I wanted to talk about this example first to make sure it's absolutely perfectly clear in your mind. What do we mean by a group, and what are we trying to do? We are looking at we're going to take this small group here, and we're going to compute the mean. We're going to take this group, we're going to compute the mean, you know, the x bar. This group, we're going to compute the mean, otherwise known as the x bar. And that's what we're comparing, but we're not going to compare them directly. We're going to compare the variances, and you'll see that formula here in just a second. Okay, now this formula or this paragraph here is very confusing, but it's also very, very important. Okay, so let's read it. Okay, within the f-test, two different estimates of the population variance are made. Okay, so the population would be all of the cars. You know, let's just narrow it down to the United States. All the cars in the United States, we have small, we have sedans, we have luxuries, okay? So those are all of the cars that we're interested in, small, sedans, and luxuries. And we're going to take a sample of each of those types. We're going to have a group that we call small. We're going to take a sample. We have a group we call sedans. We take a sample. We have a luxury. We take a sample. Okay, so we're taking a sample from that population of all of those. Okay, all right. So we have two different estimates of the population variances. The first estimate is called the between group variance. Okay. And it involves finding the variance of the means. My gosh, what the heck does that mean? The second estimate, the within group variance, is made by computing the variance using all of the data, and it's not affected by the differences in the means. So, you know, what's going on here is that we're going to have a fraction here. We're going to have variances between the groups and variance within the groups. The top guy here is we're looking at the three groups that we're talking about. So that's why he says the variance between the groups. We're looking at the X bar for the small, we're looking at the X bar for the sedans, we're looking at the X bar for the luxury, and we're saying, well, how much of a variance is there between those groups? Okay, that's the numerator, that's the guy on top. And we'll see the formula here in just a second. On the bottom, we're talking about variance within the group. So that preposition, the within the group, is the hard one. That's the one that makes you crazy. Other authors will call this pooled data. Pooled as in P-O-O-L-E-D. Pooled as in all of the data is put in the same pool. You put it all in the same pool, or the same I don't know if you call it a category or what, but you put it all in the same pool and you look at what the variance is within all of the data points. So that's what he says right here. The second estimate, the within group variance. Look at the definition, if you can read it. A variance estimate using all the sample data for an f-test. Well, that's what I mean by being pooled. We look at all the data. We don't just look at the means, okay? It is not affected by differences in the means. So it's you compute the variance using all the data. It is not okay, that's what I just said. Okay. Now, think about it. If there's no difference in the means, if this top guy, you know, there's no difference in the means, okay? All right, there's not much of a variance between the groups. Okay, it will be approximately equal to this guy down here. It'll be approximately equal to the variances within the groups. So that means that the f-test value will be approximately equal to 1. So guess what? You're not very surprised, are you? Okay, you're not very surprised because there's not very much variance in the means. Okay. Now, remember, when I say surprise, I'm talking about how surprised are you if the null hypothesis is true, okay? And then you do not reject the null hypothesis. If they differ significantly, then the between group, this guy up here, is going to be larger, and that'll give you an F value that's much bigger than 1, okay? And then you do reject the null hypothesis. So we'll explore that here in just a little bit.